to put a base. I skipped your Hello, everybody. Am I audible? One of you can reply back, maybe.
Yes,
Yep, I can hear you.
You're good.
Thank you. Thank you very much. Yeah. So we had a homework one due today. I noticed I just checked about half an hour before I came into the class that we are about 50 to 55 students. So more than 45 of you had submitted successfully. I got a few emails, about 3 to 4 of them, saying that you were not able to upload multiple images. What I recommend is, or I shouldn't say that I recommend. What I've heard from other students doing is they seem to be using what is called Cam Scanner. That's an app on a phone, or Office Lens. That is a simple scanner. So look for apps that can scan a file. Basically it takes images and converts it into PDF file, and then you can save it or send it as an email to yourself, and from there upload it. So a few things or few options there. Right thing to do will be to ask your friends. That's the best to do. And since I'm watching the computer, I see some Adobe Scan is also free and works well. Yeah, thank you. So ask each other, or share your ways on the chat session. Maybe it will be useful for others. Yeah, so that's something for what next. We have homework. I posted homework 2. That's due next Tuesday. So that's September 1. That's Tuesday, again, the usual process. We have midterm 1 scheduled for September 8th, which will be 2 weeks from today. This will be uploaded, and I'll be able to tell more details as we proceed, but it will be pretty much like your homework. Questions, everything will be very similar, except that there will be a time constraint in the sense it will be opened, the homework will be opened right during the class session, and it will be due right during the class session. So make sure you have ways to scan your file and so on during the class period. So that's something about the midterm. What else? So I did mention about the file submission, and there was a question about physics help test. It has been reasonably popular in the past. This semester also, this is going to exist, but as of now, it has not been decided how they are going to do it. But I did ask the physics office, and they do plan to do it. But the students or the teaching assistants who will be doing it, they haven't really found the right way to do that. Most probably, it will be done using a Zoom room. So look for will be updated. How about that? It will be updated on course page. As of now, I don't know exactly how it's going to happen, but most probably on a Zoom platform. So that's physics help desk. And one more question I've heard from interaction with a couple of students is about the textbook. Not everyone has access to the textbook yet, and what I've learned is that if I opt to post old edition, by old edition I mean the 9th edition. From what I understand from an email I received from the library, I am allowed to post one chapter at a time behind password. That means to say on D2L. So what I might do is I will give a link to D2L and post chapters, individual chapters on D2L. So 9th edition chapters. is scanned. Scanned chapters will be posted on Teachable. I'm just waiting so that to hear back. I want to confirm that I'm not violating any copyrights there from an email I got from the library. Most probably this is true only for this semester, since due to all the things that's going around, apparently I'm allowed to post one chapter at a time on Teachable, especially the older edition. So you can look for that as it comes by. That's it. Any other questions you guys have? Anything specific that I should point out here, or I can try to answer? Okay. If not, let me proceed. We will do chapter 2 today, basically how things move. So it's going to be an important part of the whole semester. So move. Yeah, so what we want to talk about today is how things move, or more importantly, what is this whole course about, or in very broad terms, what is physics all about? In a very simple sense, we are trying to predict things. In what sense are we predicting? Yes, we are going to predict the future, but not in the dramatic sense of what's going to happen in someone's life. That's too hard. But in very simple sense of, if you throw a ball up, after how many seconds is it going to fall back? That's also a prediction, a small kind of prediction, not something as crucial as life, but a simple prediction of that kind. For example, if you throw a ball, at what angle should you throw the ball so that it can reach a specific place at a specific time? This can be extended very easily, very dramatically, that you throw a stone very fast at the right angle, and you can go all the way and reach Mars, and you know exactly where it will fall, exactly to the extent of maybe miles, right? You make an error of a small centimeter here, and you make a significant amount of error of where it falls. So that's the kind of prediction we're talking about. And it's, believe it or not, it's the same equations that you're going to study today here, or for that matter, the course here, that actually takes spaceship to other planets and all across the space. Of course, engineering matters a lot there. So there is a lot of error correction you have to do. So it's not extremely, or it's not completely right to say that it's exactly the same equations, with a lot of modifications. But at a very basic level, it is the equations that we are going to talk about. So since we talk about prediction, so prediction has to do with something in the future, right? So future and past becomes a reference now, and that involves time. So the first point we have to talk about is time. So it's time. So we're dealing, so that is a variable called time, and usually we will use the letter t for that. So small t for time. If whenever we talk about time, for example, we say that it is 5 seconds. Now, it is with respect to something. You have to begin the clock sometime and then ask that, okay, it has been 5 seconds since I got out of the room, or it has been 5 seconds, or it has been 10 minutes since I have been driving the car. So it is always with reference to something. So that means that's called the origin. So there is always an origin associated with this. So it is not t that usually you talk about. It is a change in time. And let's say the origin is called t initial. So it is t minus t initial that you always talk about in physics, let's say. And we always go forward in time, right? We don't go backward in time. So t final minus t initial is always positive. So that's a very distinct difference between time and space. Like if I'm standing here, I go left and then I go right, right? I can go both directions, right? In space, I can go forward and backward. There is nothing that stops me from doing that. But time is very special. It's distinct from position in the sense I can only go forward. I cannot go backward in time. So in that sense, that's special. It won't play a very significant role in what we will be talking about here, but you should realize that if the time comes out negative, then something is going wrong in your calculation. So there will be often calculations where you'll be probably asked how much time does a stone take to go up and come down. If it comes out negative, make sure you're making the right interpretation. So that's something to keep in track. So again, we are going to be talking in terms of change in time. So it is t minus t initial. So often it's easy to choose your t initial to be 0. Otherwise, just let's call it delta t. So instead of talking about t alone or 2 times t minus t initial, we will be interested in the change in time, which we will represent by the letter delta. So this is a Greek letter a letter in the Greek alphabet. That's capital delta. So that's going to be time. We will measure time in seconds or minutes. So S will stand for seconds or minutes or in hours. Seconds is the unit of choice, but that doesn't mean that you have to always work in seconds. Often in your questions, it is convenient to talk in terms of seconds. So we will always work with seconds, but that's not a very strict rule. You can talk in terms of minutes and hours too. So that's time. And next is position, right? We said we are going to talk about predicting. So we will be talking about predicting where something would be. Like where would the car be if it is driving at a certain speed on the highway? How much time will it take to reach somewhere else? So it's that kind of predictions we are doing. So we are talking about position. So the next variable we will be talking about is position. Position, often the letter used is X. Doesn't have to be X, it can be Y also. Right? Often it is X or Y or Z. It could be any one of those letters. That's the most popular ones, but it doesn't mean that you should always be using X, Y, and Z. You can use S, for example, or you can use R. So there are various variables used. For now, let's use X. Again, like in time, we talk about change in position. It is not the position alone that matters. It is a change in position that we are interested in. It with respect to some initial position. That's X initial, and that's delta X. Same thing as time. We are interested in delta X, change in position. We'll measure X in meters. This shouldn't be confused with minutes. So it is going to be in meters. That's going to be the unit of choice. But we can also work in kilometers or sometimes even in miles. Often we will stick to meters or kilometers. Miles, since when we are driving on a highway, we are very much used to the idea of a mile. We have a much more intuitive feel for how much a mile is over how much a kilometer is. So sometimes we will talk in terms of miles, but the unit of the choice would be meters. So whenever you don't know which unit to use meters. Right? In an answer, you don't know which unit is the most convenient to report in, go by meters. But if you prefer, and if you know what you're doing, either way is okay. Talking about delta X, let's specify something. Let's say this is a position. Let's let me go horizontal. So this is horizontal, and let's say this is X initial. and you're planning to reach somewhere here. So that's x final. So you start from here, you go there. So there are two ways of reaching here, or there are many ways of reaching there actually. You could go all the way directly. You start from x initial and you reach there. So that's straightforward. Then what is delta x? You subtract x final minus initial, the final position minus initial position. It doesn't have to be always to the right side. Final position could be on the left. Then delta x is negative, right? If x final was equal to 3 meters and x initial was equal to 5 meters with respect to some origin, then delta x is 3 minus 5, so that's equal to minus 2 meters. So delta x can be negative, right? There is also the possibility that you could have gone all the way, reached some point here. So let's say this is x prime, and then return back. That's another possibility, but it doesn't matter. As far as change in position goes, it's only the final minus initial that matters. It doesn't matter where you go and come back. For that matter, you could have gone to another galaxy and come back. No one cares. As for, at least in this context, no one cares. You go and come back. It's a final point, that final position minus initial position. That's and this delta x in that context is said to be displacement. And we will always use displacement. If we are not using the idea of displacement, if we're not actually using the final minus initial, instead we are going all the way, it depends on the curve or the path you have taken, then we will specify it. By default, always it is going to be displacement, final minus initial, and it can be negative. Right? If something is going vertically up, that's also perfectly fine. So for example, if often we will talk about a stone being thrown up in the air and then it comes down. So this could be your x initial. If I choose x to be upward, here I chose x to be horizontal. I can also choose x to be upward, or y could be upward, either way. So if I say this is x, so this is x initial, and this could be x final. Or let me say this is x final and this is x initial. Right? So this is a ruler if you want, and this could be representing a house. So this is ground, and this could be a building. So you're standing on the roof of the building and you could be throwing a ball up in the air. So you throw a stone up in the air and then it comes down. And you can ask, what is the change in position of this ball or stone that you threw? It is final position, that's here, and initial position, that's here. So let us say this is 0 meters. And this could be 10 meters, and the highest point it reaches could be 15 meters. Right. And you could ask, what is change in x when the system is, or when the stone is going from here to there? Delta x is final minus initial. Final is 0 minus initial, that's 10 meters. So that's minus 10 meters. This depends on the choice that our x is going upward as positive. That's not necessary. That was a choice I made. I can choose any coordinate system I want, and someone else might change the whole axis altogether and say that I'll start measuring downward. So there could be another ruler here, for example, here. So one could say this is 0 meters, and this could be minus 10. Or this is 10 meters, right? This is positive in the downward direction.
Are you able to move your camera down more?
Oh, camera downwards. There, is it? Okay. Let's see. Better?
Yeah, that's better.
Okay, let me know if this happens. Okay, so this is, so earlier I had, is that visible? Yeah. Earlier I had the positive direction upward. This was 0 meters, 10 meters, 15 meters. And I can also have, let me keep this the same so that there is no confusion as to maybe it is the measurement points that is right. It could be same 0 meters. No, I better put it. This is a choice. Yes. So this is 0 meters, and this could be 10 meters. Right? So that's going downward. And one might think that, oh, does this change? Yes. So now delta x now is equal to x final minus x initial. That's a final point. So that's 10 meters minus 0 meters, and that's plus 10 meters. So your the displacement depends on your axis. Right? So you'll always report which is your positive and negative. Often we will talk about how far does it go, how far does it go above the roof, how far does it go below the roof. So those are the kind of answers we'll be talking about. And it doesn't matter which choice you make. Having said that, if you know what you're doing, choose whichever you want. But what I recommend is that all through the course, always keep, if you're talking about a vertical motion, keep positive to be facing upward. That's just convenient, less error prone. That is the only thing. It is perfectly okay to choose it in the downward direction. If you are careful, it will give you the right answer. Answer should not depend on what choice you made of a coordinate system. And that's in general true for most of what we do here. What we choose as a way of approach should not decide what the answer is. The answer should be independent of who did it, how you did it, whatever it is should be unambiguous at that end. So that will be one of the themes. So again, two things we have introduced: time and position. Right? Change and instead of talking about time itself, we talked about change in time, and instead of talking about position itself, which I talked about change in position, which we will say is displacement. So that's two basic variables we'll be using, and using those variables, we are going to derive things now. We're going to define new things out of that. So the first concept we will define is velocity. So velocity will be defined as the variable of almost or most of the time the variable we will use for velocity is v, sometimes u, mostly v. And since we are going just in one direction, for at least in this chapter, we will either go horizontally or we will go vertically. So that will be the only two choices. We can go at an angle, but that will be, as far as we are concerned, we will choose our axis to be along that direction. So motion in one direction, that's what this chapter is all about. Later in the next chapter, we'll generalize this to motion in two direction, which can also be generalized to motion in three direction. In fact, concepts remain exactly the same. That's going to be the beautiful part of this. Whatever we learn in this chapter, with very minimal, it's almost doubling it. We have something happening in the x direction, something happening in the y direction, and the concepts involved are exactly ditto the same as we're going to do here. So again, velocity is going to be defined as change in position. We had displacement over change in time. That's it. So that's a simple idea, that velocity is change in displacement over time, rate of change of position over time. as a small detail there as to what exactly should be delta t. So let me come back to that. So what exactly what I mean by here, is there any ambiguity in defining this velocity? So let's go back and look at position and time for a specific case. So this is an, let's say, illustration. So this is called a plot. So let's think of a, so it's basically an illustration of something happening. So let's say this is a straight road, right? This could be the main street of a city, right? So this is everything falls, so it's a small town. All the important things are on one street, right? So, and this could be your home, and this could be a shopping center, right? That's a shop, like your grocery store, let's say. So two important points in the town, and both are on a straight line. And you would, so we would like to describe a simple scenario where someone starts from home, goes to the shop, and then comes back. Right? That's a very simple scenario. You wake up or you start your car, let's say, and you go to the shop, do some shopping there, and then come back, again start your car, and then you come back. This can represent your position, so that's your x, let's say. So you could say this is 0, and this could be, let's say, the shop could be a few miles, so this could be 5 kilometers, let's say. So that could be a reference there. But now we want to also see this in time. So we want to introduce time here, and time will be introduced on the x-axis. So this is going to be time. If you were to sit at home for many, many hours, your position at 1 second, 2 seconds, let's talk in terms of minutes or hours, let's say. So 1 minute, 2 minute, 3 minute, it stays the same. So for example, if you're standing in the shop and you're talking about the position versus time for the person in the shop, it will stay the same. As time evolves, the position does not change with time. It's the same 5 kilometers with respect to the origin. So that's one point. So your home remains the same as a horizontal line. As time evolves, shop remains the same. But you are going to move from here to there. So let us say at some time, so for a long time you're at home, and then you get out and then you drive a car, let us say, to the shop. And the moment your position changes, so you're now somewhere here, as far as you're concerned, you're on this road. So it is changing with time. So this will look something like this. Notice I'm not drawing a straight line, so it is actually curved. And eventually you will reach here and then stop. Again, it is curved in the wrong direction. So here it is a curve that is facing upward. Here, this is a curve. If you think of a fitting a circle there, it is facing downward. The curvature is upward here. The curvature is downward there. And then you stay in the shop for some time. You shop, right? So you buy stuff. So maybe you spend some time there, and then you start. You want to come back home, and now again there is a curve here, and then there's a curve here, and it stops. So that's a typical, so this will be called a position time plot. Let's explore this region more carefully. So there was a curve there. So let's look at this curve in a more. That's how it sort of looks like here. We don't know the exact form of that curve. Later we will know. And let's say this is time, and that's position. And we said we want to see what is velocity. Velocity is change in position. So let's say we have 2 points in that curve. So change in position is this, right? It's on the x-axis. Change in position is on this road. If you're thinking of the person who's going from everything happens on a town, the change in position is on that road. So it's on that y-axis. So that's this distance. That's that vertical distance. I took this distance and took it there. So that's delta x if you want. For a displacement from here to there on the curve, it is actually a displacement from here to here if you think of it on the x-axis. It happens in a certain amount of time, which is on the x-axis. So that's the 2 points. And that's your delta t, which can be moved upward again. Can be moved upward. So that's delta t. And what we are saying is, so this is delta t. So we have a triangle structure, but it's not really a triangle because this is a curve, right? This is not a straight line. So what we are saying is velocity is change in position over change in time. And if you think carefully, this seems to be an ambiguous definition because it depends on which triangle do I pick. So if I have to talk about velocity at this point, so velocity at this point, it depends on this next choice, right? Where do I pick my delta x? What's the next point? It could be 1 second apart, it could be 3 seconds apart, and accordingly, your definition of velocity changes. So that's not convenient. It has to be a unique velocity, and that's where the definition comes. I said I left some space here. This has to be defined in such a way that this is as close to, this point has to be as close to the first point as possible. In the strict calculus sense, if you want, it has to be very close to that. So that means to say, we will use the language limit delta t tends to 0. So this velocity is not just change in position over change in time. It is actually, it has to be defined in the true sense of delta t going to 0. That means to say that this has to get closer and closer and closer and closer. And then you would think that as it gets closer, delta t becomes 0. As you get closer and closer, that is 0, and delta x also gets 0. So it seems like this is 0 over 0. But that's well defined, even though you might think that 0 over 0 is not well defined. Usually it is not. If someone asks you what is the 0 over 0, we don't know. It is not a well defined concept. But in a certain sense, in a limit, if you think of it, then it is defined. And that's the idea of calculus. Right? So this involves calculus, which we are not going to use too much. Like this is an algebra-based course, so we won't use this idea too much. But the definition requires that. And how we will avoid it is that we will lose a lot of power if we are not going to use calculus. So how we are going to make things still work with these concepts is that we will talk about uniform acceleration, and I'll define this as we go ahead. We will restrict our considerations to uniform acceleration. And it turns out that for uniform acceleration, all this ambiguity, all this calculus is relevant, but it can be ignored completely, and still we can still survive with it. We can still have a lot of concepts in there. So we are, again, where does calculus come in? Yeah, it is there, very important, but if we have not learned calculus, we still want to do as much physics as we want. And so we will restrict ourselves to uniform acceleration. And I haven't strictly said what uniform acceleration is. We will get to that. Okay. So having said that, so what is velocity? So what we want to take home from this whole discussion is that what is velocity as far as graphical analysis goes, and 2 of your homework problems. So first problem and the second problem involves graphical analysis, and velocity in a position time plot is tangent. So for example, at any point, draw a tangent. Right? So that's a tangent to that point. Right? At a point, there is a unique tangent. Always at one point on a curve, there's a unique tangent. And once you have the tangent, this makes an angle theta here. Tangent of that angle theta is your velocity, which is also called slope. So in your homework 1, problem 1, it is asked that, first of all, you have to draw some, no, I think it's in second problem, you're asked to plot something, and then you have to estimate the velocity. So what you want to do is, at the given time, you want to draw a line, estimate the angle. It doesn't have to be exact, just visually look at it and say that, oh, this seems like 30 degrees, 40 degrees. So within that error bar, you have to estimate that angle, calculate tangent of that angle, and that gives you the slope. So basic idea is that for any position prime graph, the slope of the line on the position prime graph gives you velocity. So that's one thing. So we have defined velocity now, right? The velocity is limit delta t tends to 0 of change in position over change in time. But for our purposes, this is the correct version. For our purposes, since we are not going to be using calculus too much, for the very restrictive set of problems we are going to deal with, it's going to be delta x over delta t. So that's good enough. So that's velocity. Okay, so that's velocity. So that's a new concept we have learned, right? So time and position are the two variables, and velocity is a derived variable, or a definition involves that. And we will come back to this very quickly. Next is acceleration. And what does physically, what do we mean by velocity? Pretty much what do you see on the, I mean, these days we are all familiar with cars. We see the dashboard of a car very much. So one way to see it is the odometer reading that you see. That's actually the velocity of the car, how fast it is going. How does it measure it? How many times does the wheel turn in a unit of time? Let's say in 1 second, right? Or let's say 1 minute. That's easier to measure. In 1 minute, how many turns does the wheel go around, right? That's a measure of velocity. So distance is how many times means how many circles, right? Circumference of the wheel times how many times does it go, that gives you a distance, divided by the time, that gives you a velocity. And there are sensors and instruments that can actually do this, and that's how you measure the velocity of a car at some mechanical level. And that's going to be our velocity. And most of us have a notion of velocity, how fast we are going. If you quickly reach from one point to the other, most probably you have been driving very fast. Yeah, we use that in our colloquial language. So that's the notion of velocity. What is harder is acceleration, and we will talk about that. So acceleration, we will use the letter A, and that's going to be like we defined change in position over change in time. Here we will talk about change in velocity over change in time. By change in velocity, how fast are you changing your velocity? Unless you change your velocity, you're not going to reach anywhere, right? If you are at home, you have to start from 0, pick up some speed, and then you have to reduce your speed and come back to 0, right? This is slope 0 here, right? So this is not moving, so this is slope 0. Slope is equal to 0 there, slope is equal to 0 here. That means it was at rest here, it was at rest here. But to go from this point to that point, you had to change your velocity. So if you think of it as a slope, it was 0 and then it increased its velocity and then it decreased again. Right? That's how it works. And again, if you were to bring it down here, it changes in terms of, so the slope of that curve actually decides the velocity. And here now we are to talk about how quickly is that changing. This could change very quickly, or it could go very gradually. Like often we talk about the pickup of a car. So how much you press on the gas, that sort of decides how much is your acceleration. That's a physical, that's one way of getting a physical feel for acceleration. How much you press on the gas decides how much you're going to accelerate. If you're not pressing on the accelerator at all, then you're most probably gliding. And if it was a flat surface, then most probably you will go at constant speed. But of course, there will be friction, so you will gradually come to a stop. So we'll talk about those things. So change in speed. So if you're not changing your speed, that means you're not accelerating. That's the simple idea. Again, like here, we have to talk about limit delta t tends to 0. That's necessary. But again, we will be doing our problems will be very restrictive. So this will be just change in velocity over change in time. Only in this course, because we are not doing any calculus and we are going to be doing examples which are significantly simpler. One could think of this as a slope in some curve, but that is only if you were to think of it as speed or velocity versus time graph. But one could ask, how can I get the information about acceleration from position time plot? How can we get the information about the acceleration from a position time plot? I already told that velocity is got by the slope. Right? Just think of at each point a slope, that's the velocity. Where is the information about acceleration? In the position time plot, and that information is there in the curvature. Notice at each point I could fit in a circle. Right here, this is a circle here I can fit in. At this point I could fit in a circle like this. Right? At this point again I could fit in a circle here. When it comes down here, the circle is outward. So there is a circle here, and the radius of curvature or radius of that circle decides acceleration. If this radius is small, large acceleration. If the circle you can fit at some point is very small, that means the acceleration is large. This radius that I'm talking about mathematically is called curvature. Curvature is inverse of the radius of the circle that you can fit in. So in a plot, in a position time plot, the radius of curvature tells you the acceleration. So whenever you have a position time plot, you look for two things: velocity, slope, and curvature, how much it bends, right? Intuitively, how much it bends, how strongly it is bending tells you acceleration. That is also the idea of is the circle facing downward or upward, and that also has the direction of acceleration. Here you're increasing your speed in the positive x direction. Here you're decreasing your speed. So there is an increase and a decrease we are talking about. So let's define acceleration here versus deceleration. Irrespective of what your coordinate system is, acceleration is when velocity and change in velocity, which is actually acceleration itself, are in the same direction. Right? So they are both parallel, so they are both in the same direction. Whenever that's the case, it could be downward also. If you're going downward along an axis and acceleration is also downward, then you're accelerating. Deceleration is when velocity is opposite to the is opposite to acceleration. So velocity could be this way and acceleration could be this way. So this is velocity, that's acceleration. Another possibility is that both is downward. Right? That's velocity, that's acceleration. This is velocity, that's acceleration. That's one example. Or we could have velocity is going downward and acceleration is going upward. If you're going in one, if you restrict your analysis to one dimension, that's only possibility. Right? So either you're accelerating or you're decelerating. That's only two possibilities. Or you could have acceleration zero. The velocity is not changing at all. That's a very special case. Okay, so now we have everything that we need for a few chapters. Right? So there are 4 variables in a sense: velocity, acceleration, position, and time. So variables in our problem. So variables. So that is delta t. Oh, I should change my camera, I suppose. Yes. Okay. So the variables involved in our system or in our analysis is delta t. Even though delta t involves 2 variables, t initial, t final minus t initial, we will always talk in terms of change in time. So set one of them 0 or always talk in terms of the change. So that's only one variable as far as we are concerned. Delta x, that's the second variable. Third is velocity. But since we go from an initial point to the final point, there are 2 velocities we will talk about, right? So we will be at the initial point, there will be a velocity and there will be a final point. And those 2 points we want to differentiate. Delta x and delta t, we choose our origin in a way. That choice is already over. So now we don't have any choice left. So velocity, we cannot fix it. There's another possibility that I can choose this to be 0, but then I will have to change my delta x. So I have 2 choices based on my coordinate system of time and position. I can choose my origin. So I've used that up. So that's only 2 variables now. But initial and final velocity, in general, not 0. It could be 0. It's possible that initial velocity is 0. For that matter, final velocities also could be 0. So this is going to be initial velocity. And this will be final velocity. And there will be acceleration. Now, in principle, acceleration can also change. As you're moving in general, when you're driving your car, acceleration changes at every instant. It keeps changing, so that's a complicated system. But I said that we are going to be doing simple problems. We are not going to be doing calculus-based problem where we are interested in acceleration at every point. Instead, we will talk about uniform acceleration. That means A will be uniform. That means it will be a constant. So uniform, or it will be constant. It doesn't change. In a particular problem, we are going to be discussing problems where it doesn't change with time. Acceleration remains the same, and that will be called motion under uniform acceleration. So that's one kind of problem we'll talk about. And what will be your goals, or what are we learning here in this chapter? Given a story, I say it is a story, given a physical system, a car could be driving from one point to the other, a stone could be dropped from an initial point or from the roof and it reaches the ground, or you throw the stone up in the air. Different systems, which let's say they're different stories, our goal will be to identify these 5 variables. that will be one of the hard things, that to identify these 5 variables. That will be a significant component of what we are learning here. And since we have 2 definitions, it will turn out, so in all the problems, there will be 3 variables out of this 5 will be given. Again, we have to identify that. So the skill we are learning here is that to read a problem, or to, or if we are modeling something, if you are making an analysis of what will happen to a system, we are actually trying to identify these 5 variables, and we are going to find out what are the 3 variables that is either given in a problem, or if you're doing research, what are the 3 variables that I could measure in a lab. And once that is known, there are 2 remaining variables, and our equations allow us to predict them. This can be predicted, or that means to say that this can be determined. Using our equations, we will be able to determine 2 of the 5. 3 we have to measure. We have to be in a lab, and we have to actually measure these 3 quantities. When you're working on homework problems, that means to say that 3 variables are given to you. Right? So since at least for some time we are talking about assessment, here it translates to given 3 variables, find the 2 others. But if you're in an actual real life setup, you are thinking of 3 variables that can be measured. For example, from when you're going from here to Mars, not everything is measurable. For example, as simple as distance. What's the distance between here, Earth and Mars? It's not easy to measure. Right? You cannot take a ruler and measure the distance between here and Mars. So there are a lot of unknowns. So you have to look for things that is available to you, and you have to look for things that you can actually determine using your equation. So that will be the mode of what we are working in. So there are 5 variables. That's the important point here. And let's see what are the definitions we have involved. So there are 2 definitions we have introduced, which relates some of the variables, and that is, first is velocity. Right? I define velocity as delta x over delta t. It was supposed to be limit delta t tends to 0 of that ratio, but we said we will be slightly sloppy. We will actually just talk about that ratio, and we will restrict our analysis to systems that allow that identification. It also turns out for uniform acceleration, so since we are only for this kind of motion in the simplified scenario, it is true to say that this is also equal to V final, the average basically of the velocities. That's not very obvious why that should be true, that the initial and final velocities when average should give you the velocity. It is true whenever that's uniform acceleration. So this is another small piece that we won't explore too much. One can do it classically, but do it graphically. But for the moment, let us just accept that velocity is always at any point, whenever you go from an initial to final point, it is the average of this 2 velocities. Okay. So from that point on, so then I'll stop writing the velocity. So change in position over change in time is related to V initial plus V final is equal to the average velocity, if you want, average between the initial and final. In that sense, the average velocity. So this involves 4 variables out of this 5, right? Delta x, delta t, V final, V initial. And there is no acceleration showing up in this because it's a definition. Definition of velocity does not involve acceleration. What about acceleration? Acceleration is change in velocity, which is V final minus V initial. Change in velocity over change in time, which is delta t. So that's your 2 equations. And that's the idea that 2 equations and there are 5 variables given to us. That tells you that if you're given 3 of them, I can use this equation to find the other 2. Right? And this involves in some form 5 of them, but not both of them have 5 each. Each one of them incorporates 4 of the variables and in a coupled manner. So now we want to manipulate these equations to get some more equations, and that's what we will be working with. So it's going to be a little algebra now, but you will notice that it's not going to be very complicated. So let me rewrite this equation. So let me multiply this 2 to the numerator there. I can cross multiply an equation, right? So let me rewrite this equation as V final plus V initial. That's the right hand side. And multiply the 2 on this side and write it on the other side. So it is 2 times delta x over delta t. It's the same equation. I just took the 2 onto the left and then swapped the sides on which these variables are. And I can write an equation that things on the right hand side or left hand side, it doesn't matter. 2 is equal to 3 also means that 3 is equal to 2. Right, so something like that. Same thing, do it here. Cross multiply. This is 1 here. So this is V final minus V initial is equal to, when I multiply A and delta t, so that's A times delta t. The manipulations that I'm going to do is mostly for deriving some equations. I won't be asking you how to manipulate, but it is also expected that you should be familiar with these manipulations. I don't expect you to be able to do that out of your mind anytime, but you should understand the steps that is involved. That is expected, but most probably I won't be asking you to repeat these steps. But having said that, in an actual problem, it won't be in terms of variables. You will actually put in numbers and you will be practically doing the same thing. I'm just simplifying your work by actually doing it for once. So there were 2 equations which I rewrote here, and now I'm going to derive more equations. So there were 2 definitions. I'm going to derive more equations. So how do I do that? If these 2 equations are valid, I can always add these 2 equations. Right? That's perfectly well-defined thing to do. So when I add, notice one is with a positive, other is with a negative sign that cancel out. So it is 2 times V final is equal to 2 times delta x over delta t plus A times delta t. Right. I had 2 equations, basically definition of velocity and definition of acceleration. Those were the 2 equations. I rewrote them in a certain form, and then I just added them. If the individual equations are true, the added equation should also be true. And then what I do is I divide each term by a factor of 2 and multiply by delta t. So notice what I'm doing here. So it is dividing by 2, multiplying by 2. So this is V final delta t. So I multiplied by delta t divided by 2. If I multiply by delta t, that cancels out. Divide by 2, that cancels out. So this is just delta x. And this is plus, I divide it by 2 and multiply by delta t, that makes it a square. And that's going to be an important equation, but not in this form. Let me write this to the left. Okay. So I'm going to write this equation as delta x, which is on the right. I'll take it to the left and everything else to the right. So this is the final delta t minus, notice a minus sign, that's important, half A delta t squared. Don't be overwhelmed. Seems like too many equations. We will, when we are analyzing this will become much easier. It's to make things easier at a later stage that I'm deriving this equation. That's going to be our equation, right? One of the equations. So let me box them. So I had one equation here. Let me write. So this is our first equation, right? Which I rewrote it in this form. And this could be your second equation. This is fine, but more popularly it is written in this form. These two were definitions, and I derived an equation of this kind. Now, when I'm doing this, I added these two equations. I could have actually subtracted these two equations. If I had subtracted them, the initial would have added and the final would have subtracted out. And here, instead of adding, I would have subtracted this. So this would have come with a negative sign, and all the initial velocities would have become a final velocity, right? And this steps would have gone the same manner. And the equation I would have got that manner would be the same, pretty much the same, except that final velocity will be initial velocity, and acceleration here would have a positive sign. So that's your fourth equation. And we are going to use this sufficiently that you will sort of remember this by a few weeks. So these equations will be given to you. First of all, this will be available to you, but this is an online course, so we won't be having closed book exams. But if it was a closed book exam, like I used to have before the semester, then I give an equation sheet which has these equations in it. But otherwise, these equations are the important ones. The equation sheet is still available on the web page. It is a good idea to use those equation sheet while you're doing the homework. It limits the number of equations available to you, so you don't have to look around for which equation you're working with. So that's 4 equations, but I said there are 5 variables, and whenever there are 5 variables, it's good to have 5 equations. Another possibility was I added, subtracted. I could have multiplied these 2 equations, right? I could have multiplied these 2 equations. This is this is a sum of 2 variables, difference of 2 variables. When I multiply the sum and difference, remember your algebra, x plus y times x minus y is actually x squared minus y squared. Right? So if I were to multiply these 2 equations, I'll get v final squared minus v initial squared. So that's v final squared minus v initial squared. And if I were to multiply the right hand side, the delta t actually cancels, and you simply get 2 times a times delta x. So then I probably went a little quick there, but the point is I have 5 equations. And let's try to analyze those 5 equations and how we use that in our problems. So let me switch over and let me erase the board.
Could you by chance slide back over to the other equation real quick, please?
Oh, sure.
Thank you.
While I'm erasing, that's a good thing to do. Yeah. Good. Okay. Okay, are we good? Shall I move?
Yes, thank you.
Welcome. Okay, so let me write those equations down again. So that is delta x over delta t is equal to v final plus v initial over 2. Second equation can be written in this form, v initial plus a delta t. I wrote v initial on the left hand side when on the previous board, but I took the v initial on the other side. There is another equation, delta x is equal to v initial delta t plus half a delta t square. And then there is delta x is equal to v final delta t minus half a delta t square. And finally, we have v final square. Again, I took v initial on the other side. V initial square plus 2a times delta x. Okay, so that's good. So we have 5 equations, right? And even though it might be overwhelming, too many variables, it might not be very intuitive at this point, but you'll get comfortable with these equations as we proceed. One thing is that there are 5 variables. There is a missing variable in each one of these equations. That's something to realize. Right? Look for the 5 variables. Let me write that down here. Delta t, delta x, v initial, v final, and a. Right? In each one of this equation, there's only one variable missing. Let's look at the first one. Delta x is there, delta t, there is no a in this. A is missing. Right? In the second one, delta x is missing. Third one, v final is missing. Fourth one, v initial is missing. And in the last one, time is missing. But that does not mean that if you're asked to calculate acceleration, you should use this. In fact, that's a bad idea, because if there is no acceleration in this equation, how are you going to determine the acceleration using that equation? So first thing to do is that if you're being asked to find a variable, look for this. It's surely not that equation that you want to check for. So that's one thing. So how do we go about doing this? In any problem, so there will be 3 variables given, right? So, there is, so 3, strategy, let's say strategy. Is this still visible on the? Yeah, it is.
Yeah, it's
Yeah, you're good.
So, so the strategy is that first step is identify or recognize, identify 3 given variables. In homework problems, it translates to saying given, otherwise it is 3 quantities that can be measured, right? That you can decipher from some measurements, right? So out of 5, you're already knowing 3, so there are remaining 2, right? But one of them is asked for. What is the unknown variable? Notice the difference between unknown and the missing variable. Unknown variable is what is being asked for, a quantity asked for. For example, what's the acceleration, right? That means that's the variable that we are looking for. So 3 variables you're given. One is being asked for. The last one is the missing variable. Is the missing variable. So whatever is not entering in the discussion at all is the missing variable. And that's crucial because that's the equation you want to use. Use that equation. Use the equation that does not involve the missing variable, or that means to say this column, right? Identify the missing variable. That's the equation you want to use. That's it. And that's the key piece. And from that point, it is just putting in numbers and calculating the unknown. So let's do an example, right? So to tell you how this works, so let's do a very simple example, and we'll come back next time and do more elaborate examples, right? So a car starts from rest and accelerates uniformly, let's say. So often we don't use it, but it's understood that in this course, we are always talking about uniform acceleration, and accelerates uniformly with 2 meters per second square. Notice the units, this was a velocity over time, so it is meters per second for velocity, and there is another seconds there. So acceleration is always 2 meters per second square. A car starts from rest and accelerates for, let's say, a distance of 50, or let's say 150 meters. Okay. And the question is, find the time data. Let me make it simple. Find the final velocity. I have 4 minutes remaining, so I should try to make a simple question. So find the final velocity. And by final velocity, I mean the velocity once it has finished 150 meters. So it seems like, so now first the point is you have to identify all the variables, right? So a solution is first write down all the variables, delta x, delta t, and v initial, v final, and acceleration, right? First write down all the variables that's given to you. So it seems, and remember, we have to have 3. If you're not given 3 variables, the question, either the question is wrong, or you're not gathering, or you're not interpreting the question correctly. So delta x, that's 150 meters. So let's have a diagram here. So that's starting from here, that's here. So that's x initial, that's x final. So that's 150 meters. And let's say this is positive direction. Right? So that's plus 150 meters.
Can you move the camera down again?
I arrange this properly this time. Okay, so let's see. Better?
Yep.
Okay, so I hope you guys didn't miss this while I was doing earlier. So there was delta x 150. I chose this to be positive direction. I could have chosen this to be positive direction. I chose that to be positive. So this is 0, that's 150. So that's 0, that's 150. So that's positive 150. If by any chance I had chosen that way, then I would have said it is minus 150, and accordingly things will change. That's perfectly fine, which choice you make. So that's plus 150, and time is what is being asked for, right? No, that's not what is asked. Find the final velocity. This is what is being asked for, right? That's the unknown, if you want. And delta x is here. Acceleration is given to you. And since since it says it's accelerating, so that means it's in the same direction as velocity. So if you have to start from rest and reach there, it has to have velocity in that direction. So it's plus 2. So there's an interpretation there of why is this plus or minus. We will do more examples and get that cleared. So that's something you should inquire. So like extra credit, right? So I should give you some extra credit problems for today. So extra credit problem is, why is this positive? Think of a scenario where this is negative, right? So write something about when this would be negative. That's your extra credit. Okay. Consider a situation where acceleration will be negative. That's 2 quantities given. What is the third variable? I cannot proceed if the third variable is not given to me. Where is the third variable here? That's the question. So can anyone answer?
Is it rest? Is it 0 time?
Yes, good, very good. So notice sometimes the information is given in words, right? In the problem, it says that a car starts from rest. So you have to be recognizing that. So initial velocity is 0. Great. So now we have 3 quantities given. Now, what's the strategy here? Strategy is not to look for the unknown. This is the missing variable. One is unknown. This is the missing variable, and that plays an important role in the sense that it tells you which equation to use. Delta t missing, you use this equation. So I immediately write down this equation. That's the equation that's going to help me get to the solution. Once you have the equation, put in the numbers. V final is what is V final square. V final square V initial is 0 square plus 2. A is 2, so that's plus 2. And delta X is plus 150. That's it. So 2 times 2, 4, 4 times 150, that's 600. But that's V final square. So V final is square root of 600. And its units, bring the units out, so that's meters per second. Square root of 600 is, across the time, I'll just write this and stop. Oops, square root. And that's about 25 meters per second. Again, just to repeat, identify the 3 variables that's given to you, find the unknown, or identify which variable is being asked for, then recognize the missing variable. That's crucial because that tells you which equation to use. So write down that equation, plug in the numbers immediately because there will be one unknown, rest everything is known. And that unknown will give you the answer. So recognizing the equation is what missing variable is about. We'll do more examples next time. It hopefully will get a lot more clearer than there's only one. I had time to do only one example. Thank you, and we'll meet next time. Any questions or comments? You're welcome to ask now, but you're free to leave.